So in the last segment, I referenced a conformational lab, and I think it's worth us clarifying some language regarding the levels of inquiry. I think many people, when they hear the word inquiry, think of students heading back to the lab, rummaging through the lab drawers, and somehow inventing the entire field of chemistry from scratch. All right, to be honest, that's a huge exaggeration, but I think sometimes that picture really does flash in teachers' minds at times. So I think it's worth us defining some levels of student direction in experiments. So you've now seen two experiments with different levels of inquiry in them. One was the confirmation lab or a verification lab, where students were going to rederive something that was already known to them. So in this case, it was the value of the ideal gas law constant R, and that's an example of a conformational lab. And if we look at sort of the key factors that make something inquiry, we can look at who provides the question to investigate, who develops the procedure, and who comes up with the solution to the question. And if we sort of look at these as just the main sort of features that we're going to look at, when we look at a conformational lab, when we did the determination of R, I gave my students the question. So as a teacher, I told them what the question was, find R. I gave them the procedure in excruciating detail, and then the solution comes forward mostly from the teacher. The students already knew the answer to the question. They already knew what the value of R was. They were just trying to see if they could actually re-verify that experimentally. Now, if we look back at the earlier one, if we go back to the bleach and food coloring lab, that was a little bit more of a guided inquiry experiment. So another level of inquiry you could put is sort of a guided inquiry approach. And in guided inquiry, I sort of gave my students the question to investigate. We have this bleach and food coloring, and I used some guiding questions to sort of work together with the students. So teacher and student together were working on the procedure. But in fact, when it came down to it, the students pretty much developed almost the entire procedure by themselves. I just gave them a couple of tips and helped them along the way to ensure that we had data we could compare. I narrowed it down to one wavelength for them, and we sort of clarified what were the parameters we were going to do for the second trial for each group. But when it comes to the solution, students are going to come up with on their very own, how did this affect the rate of the reaction? Did it go faster? Did it go slower? Did this change actually have no effect? So if the procedure and the solution are sort of developed by the student, then we're taking the inquiry a little further from the teacher-directed model, a little bit more to the student-directed model. So when we come back to the lab the next day, after the students have actually done the data, they've given me their bleach and food coloring lab, I go through the class and show them how to do a linear regression on a spreadsheet, and then they can actually determine whether the variable that they modified increased, decreased, or had no noticeable effect on the rate. So that's a part where the students develop the procedure, the students develop the solution, but I'm helping them do a little bit of the elaboration and giving them a little bit of extension. Now, there is a level of inquiry in between these two levels, something called structured inquiry. And if you're familiar with the POGIL project, there are many manuals in POGIL now. POGIL stands for the Process-Oriented Guided Inquiry Learning. And this is an example where you can incorporate student-directed learning in the classroom, not just in the laboratory. POGIL projects often start with data sets that are already established, and the students aren't collecting the data. They're given the data from experiments, and they're given a set of guiding questions to actually go and structure their analysis for the data. And depending on how the activity is structured, this might fall into the guided inquiry or the structured inquiry category. But usually with these types of things, the question is provided at the beginning of the activity. The procedure in terms of the guiding questions are usually given, but students are developing the relationship between the variables. They're actually analyzing the data and coming to a conclusion. And so it's more of a structured inquiry approach where you set them up that they can start to discover things for themselves, but you've carefully selected the data that they'll hopefully get to the conclusion that you want them to have at the end. Now, there is one more level. Open inquiry represents the highest level of inquiry. And in open inquiry, it's a pretty hands-off approach here. Students are going to develop their own questions, students are going to develop their own procedure, and students are going to reason through what does all of this mean at the end of it. This is a level of inquiry you may not be able to achieve in your class, or you may choose never to use in your class. But this represents a very high level here. The table that I show you here is actually modified from an article that appeared in the Science Teacher, an article by Randy Bell, Lara Smetana, and Ian Binns, and that references were included in the notes that accompany this video. But in the article, the authors labeled these as 1, 2, 3, and 4, and sort of stepping up the level of inquiry as we go along. And that if you think of this sort of as a continuum, our goal is to push students gradually into the direction of going to higher levels of inquiry. And so if you give kids a lot of scaffolding, you're probably going to be able to take them from conformational labs and start to work their way up that maybe someday they're going to be able to handle a level 4 inquiry experiment. But please, 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 do not start with open inquiry, watch it fail, let your kids flounder in the lab, and then say inquiry doesn't work in my classroom. When I think about the most complicated concepts that I teach in my advanced chemistry class, buffers and applications of equilibrium, I would never think to start the school year with those problems. They are way too complex to start on the first or second day of class. I work all year to build up the concepts to get understanding. So we start with chemical equations, we go into stoichiometry, then we cover reversible reactions, we talk about major species of solution, concentration, and kinetics. And so when we get to things like buffers, students already have the skill set that they need to be successful. If you think of inquiry the same way, you need to start building the skill set early and start to build kids up to the point that they can handle something like an open inquiry experiment. So I want to give you an example of a lab that involves a greater level of student direction. I would hesitate to call this all the way up to open inquiry, largely because in this experiment I am giving the students the purpose of the experiment, which is to determine what the activity series of metals is for a very carefully selected group of metals and their ions. I start this activity in class by demonstrating the reaction of mossy zinc with tin 2 chloride. The tin 2 chloride solution has actually been acidified with hydrochloric acid. And if you want to see that demonstration, there actually is a video in the Flynn e-learning series. Look for the title of Floating Tin Sponge, and you can find the actual demonstration and analysis there. But as I'm going through that demonstration, I'm asking kids all kinds of questions. We see bubbles being generated. I ask them what are the possibilities of what could be the gas inside of those bubbles. And then we work to the point of figuring out that it has to be hydrogen through a variety of tests. And then as a class, we have to come to some kind of a consensus as what we're going to call more reactive. What makes this metal more reactive than that metal? And we eventually settle on a definition. I make sure I steer the conversation in a direction where we say, well, we know metals when they make ions and react that they lose electrons. So the metal that's more likely to lose its electrons must be the metal that's more reactive. And then I give my kids a setup of 3 metals and 4 nitrate solutions, and they have to find a way to rank those 4 metals in order of decreasing reactivity. And so the metals that I give them lead, I give them copper, and I give them zinc. They have access to silver nitrate. I have it set up for them in the lab with dropper bottles, or you could use barrel pipettes as well. And then they have copper nitrate, copper 2 nitrate, zinc nitrate, and lead nitrate. And so they have to go back into the laboratory and figure out a series of steps that's going to allow them to get to classifying one metal as more reactive than the other. The brainstorming part happens in the classroom, so I don't do that actually in the lab. I don't actually even let them go back into the laboratory until after I've already verified the procedure. So they start to put ideas together, they bring the procedures to me, and then I just give them instant feedback on it. I often am saying, is that step really necessary? Could you actually eliminate one step? Are there tests that are redundant? So the least efficient way that students can do this, there's 4 solutions, there's 3 metals, you have 12 possible combinations. And so there is a really least efficient method possible, which is to test everything with everything. That's never good enough in my class, and so I don't let them do that. If they come up to me and say, well, we'll just put all the nitrates and all the different metals and we'll be done. And I say, do you really need to do all of those steps? Is every single one of those absolutely necessary? And eventually they come to the point that, well, if I have lead metal, I probably don't need to react it with lead nitrate because lead and lead aren't really going to do things to each other. And so we at least get to the point of eliminating one step. And sometimes, depending on how much time I have that particular year, I'll say also, are there other steps you can eliminate? Can you get this down to the fewest steps possible? And so kids are actually evaluating themselves in terms of their procedural design. Did I really need to conduct that step? After I've tested copper metal with zinc nitrate, do you also need to test zinc metal with copper nitrate? Or is that step redundant? Have you already figured out the outcome? And so by going through the series of steps then, students can come to the possibilities of trying to get there in the fewest steps possible. Some years I've actually given extra credit to the group that can get to the correct answer with the fewest steps possible. But they actually have to arrive at the correct answer. They have to document every step. But it's another level of challenge you can give your students if they're ready to go that far. So I do want to show you a little bit of what does happen when you combine some of these together. You get some pretty dramatic reactions. One of the things that I'm also doing as I'm evaluating the procedure is I'm talking about quantity. How much of the metal do you need? How much of the nitrate solution do you need? They'll say put 10 milliliters or 100 milliliters of solution down and 20 pieces of metal. I'm like, well, are you going to get the same reaction with one piece of metal and a couple of drops? Let's really think about conserving resources here. And so I just have them, after they've actually gone through and given me a procedure that makes sense, they can go back to the lab and they can actually test out the outcome of their experiments. The nice thing about this particular experiment, making it as open of an inquiry as I can, is that the procedure itself, putting metals into a dish and putting solutions on them, this data collection is maybe 2 minutes long. The data doesn't take long to acquire. What takes long to do is actually develop the procedure. And that gives me lots of time in the classroom setting to actually have them refine their procedure until it's a very effective procedure, one that's going to get them a result that makes a lot of sense in a very few number of steps. Now I'm going for the least efficient method here. You absolutely can do this in fewer steps. I've had groups do it in as little as 3 steps. But you have to get lucky on your first trial. You can get it pretty reliably in 4 or 5, but the more you can do to whittle down the steps, the more thinking your kids have to do. And that's really what we're trying to do in inquiry, is get kids more engaged in the thinking process, that they really analyze the system carefully, think about whether steps are redundant, think about the chemistry that they know, and apply it to a new situation. So you just want to finish up the test so you guys can see sort of on the close-up camera what each of the results of the experiments look like. But you can see that the change is pretty instantaneous upon adding the new solutions if a reaction is going to occur. One tip, if you guys are going to use this lab, make sure you steel wool the metals down before you start. You do need a fresh metal surface because a lot of time oxide layers can form on the outside of many metals. So you can see on the close-up of the experiment sort of what the system looks like after all of the reactions have been completed. And you can help encourage your kids to eliminate steps as much as possible. Now, coming out of this experiment, to build the extension piece into the lab, to get them to actually think one step further going into the elaboration and extension part, I asked them if they can take the results from that tin and zinc reaction that we did at the beginning of the class and roll tin into the activity series that they've generated for silver, lead, copper, and zinc. And if they can't, then what further tests or experiments would they have to do before they could definitively place tin into their series? So now we've already done one lab where they've designed an experiment, and now I'm asking them to fit a new system in, or if they can't fit it in, say what the next experiment they'd need to do to conduct in order to get that into their series. And so the transfer of knowledge is actually built almost right into this activity. But now when we're going to go into single displacement reactions and talk about predicting the outcome of a single displacement reaction, or the electrochemical potentials, and in the redox and electrochemistry chapter, we've already built a very concrete example that students can extend that knowledge in future parts of the course.